Hi, my name is Matthias Beckert. In today's session, I would like to give you an introduction into our second part of the application development workflow. While in the first part we focused on the CMake-based application development, the second part focuses on the deployment and the debugging of an application. So, let's start. The application deployment, or in general the application development in our VS Code-based environment, is constructed around a set of CMake tasks. And the CMake tasks will build the application, perform a connection test before we can deploy them, like checking is the target available where we would like to deploy to, and if our SSH keys are still valid. And if this is the case, we deploy our application to the target based on rsync and SSH, and while doing that, we exclude headers and debug files. The target we deploy to is directly derived from the selected preset, which we used to build our application. So let's check what is required if we would like to run an application on the target. Running an application is the most simple way of this application workflow, where we would simply, as I said, build the application, deploy it to the target, and start it via an SSH call. And you can see this very sophisticated call here on the right side, where we also have the sourcing of a target file which specifies the connection settings based on the currently active CMake preset. Again, as I said, the target where we deploy the application to is derived from the currently selected CMake preset. This is running an application. If we would like to debug an application, some further steps are required. Again, we need to build the application and also deploy the application. But since we want to debug the application, we also need to start the GDB server on the target. And when we finished debugging our application, we would also like to shut down this GDB server on the target. Here on the right, you can see the call we use to start the GDB server on the target. Again, the connection settings are derived from the currently active CMake preset. Now we have a GDB server running on the target and a deployed application. The last step we need to do is to start a matching VS Code launch configuration to really start debug session inside VS Code. The launch configuration itself has a so-called pre-launch task, and this pre-launch task is start GDB on target. So when we start the debug session, everything that I just explained with deploying an application and building it and preparing the GDB on the target, everything will happen automatically because the launch configuration references the start GDB server on the target, and therefore all the other actions happen automatically. And with this, you can simply debug an application on a different set of targets where the connection, as I said, is derived from the currently active CMake preset. So if we would now like to compare what's needed to run an application or to debug an application, the first thing we need to be aware of is that we have to select the correct application and the correct CMake preset on the bottom ribbon of VS Code. For running the application, the only thing we need to do is now press Ctrl+Shift+P inside VS Code and use the corresponding Run App from Active Build Preset task to fire up the SSH command, and then everything is happening automatically and the application will be started on the target. For the debug session, it is even easier because you only have to press F5, which will toggle the debug session on VS Code, which then will automatically start the GDB server, and also deploy the application. So, having said that, let's have a look how this looks and feels in a running system with a real target. Again, we take the MyJSON application, which is part of our workspace. And we would like now to execute this application as part of a target image. And the target image we now would like to use is located under /workspace images AMD64 appdev QEMU crinit, which means that we are starting an application development image in a QEMU instance for x86, and it has crinit as an init daemon. In order to do that, for me, this now means that I have to take the correct command to start the image. For me, this is make QEMU. For you, this might depend on your build system, which could also be a task-based build system. And I press enter, and this now starts the QEMU instance, which I would like now to use as my deployment target. In order to deploy the application, we have to select which application we would like to deploy, and this can be done by the bottom ribbon here of VS Code. So let's select the correct application here, which again is MyJSON app. We also select the correct build preset, which is QEMU x86, because it's an QEMU x86 instance we would like to deploy to, and that's it. Now we click on build, we update our build files, and the only thing left to do is now to trigger the tasks which deploy the application to the target and then run them. In order to do this, we simply press Ctrl-Shift-P, type in run, so that we have tasks, run tasks here at the top. We click on that, and then we type in run app, so that the filtering only shows you run app from active build preset. We click on this, and now the tasks are started, like building the application, testing if the connection is working, deploying the application, and then calling the application. And this is what you see here in this window. This was the build step. This down here is the connection test. This here is the upload. And this here is the output of the application. So the application already has been executed on the target. So let's check if the application is really on the target, because I just deployed it and I run it. And yeah, to prove that it's really there on the target, we switch here to our QEMU instance. We log in with the credentials root as a user and Linux as password. And inside here we can now also call MyJSON app. And another thing is now, since we had the app running, we may also want to debug it. And again, for debugging, it is the same as for the deployment. You have to select down here the correct application. If it is already there, you don't have to reselect it. I'm only doing this to show you what you need to do. And also the correct preset here. And the only thing left to do now is press F5, which will start the task that shall start the GDB server on the target. And this task has dependencies so that an application is deployed to the target. And when this has been handled, so the GDB server was started, the application was deployed and all that nonsense, then, well, we drop into our debug shell here. So we can really now debug our application. We can step over functions, we can step into functions. And to prove that this is really running on the target, let me switch over back to the target. We type in psfaux and we pipe the output to cat to get a better view. And what we see here now is that the GDB server is running on the target and that MyJSON app is being debugged. And when I now let the application run, it will terminate here because we don't have a loop or any kind of wait statement in here. It will terminate, and therefore also the debugging session terminates. And as a post-debug step, it will be triggered that the GDB server on the target is torn down. So if I let this application run now, we see here that we see kill all GDB server, which is executed on the target. And if I switch back to the target and I type in ps-faux pipe cat again, we see that the GDB server and the application is gone. And that's it for the application debugging. One additional feature I can show you, and that is the development of high integrity applications. In order to do that, we need to first turn down this QEMU instance. Sorry, I need to type in the correct command, which is ctl power off. This will turn down the current instance. And what we then need to do is we need to start our high integrity system. So we have a setup in our SDK where you really start a system with two virtual machines, a low integrity virtual machine and a high integrity virtual machine. And this is called EBCL FSA. This is also available as an image configuration. It's under /workspace images ARM64 QEMU EBCL FSA. And you can start it like the other image, either with a task or with make QEMU. Now, this image contains an example application. This example application is called EBCL FSA demo. And on the high integrity side, the high integrity main application is the application which is getting started right when the kernel has been started. So instead of a sophisticated init daemon, this VM really starts directly this high integrity application. So let's check what the regular output looks like. So let's type in make QEMU to start the setup. We are starting the system. Here you can see the output of the hypervisor, now the output of the first VM, and the output of the second VM is what is prepended here by VM high. So this is the kernel output of the high integrity VM, and here you see hello from EBCL FSA high integrity demo application, which is exactly this string here. And now we would like to change this. So let's type in hello from EBCL FSA high integrity demo application during our SDK recording sessions. Let's save that. We now need to shut down the QEMU instance. The easiest thing is to simply kill it. ps-faux, we see here that the QEMU instance is still running. We copy the PID and we type in kill, and the instance has been killed. Now the application deployment for this high integrity or for this changed high integrity app is slightly different, because on the high integrity user land there is no SSH daemon running, and there is also no rsync. And as a result, you can't use the deployment step as you would use it for the low integrity applications right now. What you need to do instead is recompile the application as part of the image build and then reintegrate it into the rootfs. And this can be done by recalling make QEMU in that case. But what you could also do is you could test if your application builds at all. And this can be done by selecting down the correct application here in the bottom ribbon again, which in our case is now EBCL FSA demo, and the correct preset, which in our case now is high app for high integrity app. Now we click on build and you see the application has been built. And if we would now like to see this running really in the system, we type in make QEMU, which rebuilds the application, recreates the image used by the QEMU instance, and after a few seconds, the QEMU instance will start, and hopefully we will see our new greeting message of the high integrity application on the high integrity VM. So again, we see the output here from the hypervisor. First the low integrity VM and then the high integrity VM. And here we have our string, hello from EBCL FSA high integrity demo application during our SDK recording sessions. So this is how you can update even your high integrity applications on the high integrity VM of our EBCL FSA demo image that is included in our EB Corbos Linux for Safety Applications SDK. You have now seen how you can develop an application and debug it in a running system. This running system was based on a QEMU instance, which was executed as part of the dev container. While this is nice, usually at some point in your project or your development, you will execute your applications also on real hardware. And since the networking setup with a containerized environment is always a little bit different, we would also like to give you a quick hint how you can make it work even when developing from inside a container. What you can see here on the screen is the usual setup that you have with a containerized environment, assuming now that you are using Docker. For Podman, for example, it might be a little bit different, but very similar. So what you can see here is that you have a dev container running inside your host. And this dev container usually uses VETH peer interfaces to bridge between the different network namespaces of your host and your development container. And by default, this virtual Ethernet interface is then connected to something which is called Docker 0, which is a huge bridge interface that bridges all your containers if you don't specify a specific network you would like to use. And usually you have an additional upstream interface that connects your development host to the outside world, and access from the dev container to the outside world then happens via routing on your host. If you would now like to include a target in this setup, the most elegant way to do that is with an additional interface that is dedicated for the connection to this target. And this could be a USB to Ethernet adapter in the easiest case. But it could also be some kind of virtual interface, like a virtual LAN interface or a VXLAN interface, or even some kind of VPN interface. The important part is that you add this interface to the Docker 0 bridge, so that from your development container you can directly access this interface and interact with the target. As an example, we added the corresponding IP route 2 command here. For example, if your interface that has the direct connection to the target would be named ETH1, you would simply call IP-link set dev ETH1 master Docker 0, which would place ETH1 in the Docker 0 bridge. And then you would be able to access your target from within your development container. Having said that, this is the end of today's session. Stay tuned for more updates also on our application development workflow.